Welcome back, everyone. So last time we learned about the BJT voltage divider bias, which was a circuit that looked like this. And we're going to go ahead and solve this example using our new technique. And let's go ahead and say that R1 is equal to 130K and R2 is equal to 30K. And we're going to build upon this problem next class. And let's make our RE resistor, our emitter resistor, let's make that equal to 3K. And let's make our collector resistor equal to 8K. We have 24 volts applied, ground down here, and then the base is being biased by this voltage divider, hence voltage divider bias. Okay. We talked about that there were a few different techniques for solving this circuit, and last time we covered the Thevenin solution. Today we're going to cover the approximation technique. So let me go ahead and list out those two techniques that we've learned, or one that we have learned, and the next one we're going to learn right now. Okay, so for today, we're going to cover this technique. And this technique actually works quite well under certain situations. Now, I did not give a beta for this transistor, so let me go ahead and put that to complete this problem. We're going to give ourselves a beta equal to, let's just say 150. And let's also put some conditions on when this approximation technique is most valuable. Okay, so when you have, let's say, for a voltage divider bias, and let's say if R2, that second resistor down here, if R2 is less than 0.1 times beta times RE, our emitter resistor, we're going to make an assumption that the base current is negligible. And we made an assumption similar to this previously when we solved it. But in this case, we're going to actually use that for the sake of calculating our base current and our collector current and our emitter current over here. So if R2 is less than 0.1 times beta times RE, I believe that is when you're going to get the most accurate results from this approximation technique. And I think for us, this technique is most valuable, especially when you're operating these transistors for our intended application, which we're going to talk about, which is amplification. Okay, so there's always two things that you generally use a transistor for. The first one would be as a switch to turn something on and off. And you can see this when you're working with like embedded systems. If you're taking 262 or have taken 262 and you've talked about microcontrollers, you know you can't supply that much current from a pin of a microcontroller. You know, they have a limit. You just can't supply or source or even sync, tens of milliamps. You can get away with sinking more than you can source. Generally speaking, my rule of thumb is if you're sourcing more than 1 milliamp, it needs to come from somewhere else, not inside of the microcontroller. And if you're sinking more than, say, 10 milliamps, if you have 10 milliamps or greater going into the microcontroller, then I would suggest having an external circuit to do that, similar to that base bias circuit that we did with a transistor, and we did examples controlling an LED, turning on that LED on and off, and in lab we'll also do that as well. So getting back to this, if this is the case, then it's going to give us a much easier time to approximate the Q point for this circuit, or for approximating our operating parameters. Okay, so how do we do this? How can we go ahead and solve this? Well, if we assume that the IB is negligible, then we can just solve for the voltage at this point just using our voltage divider equation. So over here we have V sub B. So all we have to do is start by solving for what the voltage is at this point. And since we're assuming that the amount of current entering this transistor is, next to 0, then this equation all of a sudden becomes valid. So let's go ahead and let's solve first for V sub B. Now, if I apply that voltage divider equation to it, I have 24 volts coming in, and I have VB, so to speak, coming out of the voltage divider that's been created here by R1 and R2. So we'll do we'll do 24 volts, our V in, times R2, which is 30 ohms. Oh, these are Ks. These are Ks, sorry, big difference. Forgot to write in the K over here. Okay, so 24 volts times 30 K ohms divided by R1 plus R2, which is 130 K plus 30 K. And that should give us the voltage here at this point. It's just the voltage divider equation. Well, what does that end up coming out to? Well, it's 4.5 volts in our case. Okay, so we figured out the voltage at this point, and now the next part is, well, how do you figure out V sub E? Okay, now from the base to emitter we have a 0.7 volt drop. So if we have 4.5 volts here and we have a 0.7 volt drop, as we do, between the base and the emitter formed by that PN junction, that diode that exists between this point and this point, then we can just subtract 0.7 volts from this and get what V sub E is equal to. Okay, so V sub E now is going to be equal to 4.5 volts minus 0.7 volts. Okay, so that's a very convenient, easy way to figure out what the voltage at the emitter is equal to. Well, what's that going to be equal to? Well, 3.8 volts. Okay, and what can we do with this now that we know that this is 3.8 volts? Well, again, we're assuming that we have 0 current entering, or that this is so small that it does not make much difference to our equation. As I said, this is an approximation technique. So now if we want to figure out what the emitter current is, so the current over here, IE, well, we can just apply Ohm's law. We have the value for the resistance across this emitter, 3K, and we have 3.8 volts across it. So we can say it's 3.8 volts divided by 3K should give us the current flowing through this emitter resistor. So we get IE is equal to 3.8 volts divided by 3K. Okay, so what does that end up being equal to? It's 1.26 milliamps. Perfect. And now again, we know the relationship between the collector current and the emitter current. Well, the emitter current is equal to the collector current plus the base current. But again, we're going back to this approximation technique where we're assuming that IB is negligible. So we can just go ahead and say that IC is approximately equal to IE. And that's equal to 1.26 milliamps. And now we have our IC. Okay, so we have our emitter current, and now we have our collector current. The last thing that we need to solve for our operating parameter is the voltage between the collector and the emitter. So VCE. Now VCE is easy to solve for because we're just going to write out a KVL loop going from 24 volts minus the voltage drop across the 8K, which we can get from the collector current times the resistance of our collector resistor. And similarly, we'll subtract from 24 volts the voltage drop across RE, which we know to be 3.8 volts. So once we go ahead and subtract these two voltages from our collector, from VCC, we will have had VCE. So let's go ahead and do that. VCE is equal to 24 volts minus 1.26 milliamps times both 8K plus 3K. Okay, so I'm just multiplying these out. This is the voltage drop across the 8K and the voltage drop across the 3K. So what do we end up getting for VCE? VCE ends up being equal to 10.0. It's supposed to be 10.06 volts. Okay, so we actually have everything that we need in order to place our Q point on a load line. We have 10.06 for our VCE, and we have our collector current. And that goes ahead and tells us exactly where we are as far as where this transistor is currently biased. So if we go ahead and finish this up by doing the load line, we're going to plot a line from IC and where it intersects with saturation, and the same thing VCE where it intersects at its greatest point, which is at cutoff. Well, okay, let's start with cutoff. What's VCE when we're at cutoff? Well, it's just 24 volts because this would be behaving as though it's open, and we would have no voltage drop across RC, no voltage drop across RE, so 24 volts minus 0, we get 24 volts at our point of cutoff. And then similarly, we want to know what IC is at saturation, or at the most saturated a transistor could be completely on, where we have 0 volts between the collector and the emitter. Okay. So if we assume a 0 volt drop over here between the collector and the emitter, what's the max current that we could have going through here? Well, it's just going to be 24 volts divided by 8K and 3K. So 24 volts divided by 8 plus 3K. Well, what does that end up being equal to? It's 2.2 milliamps. Okay, so now we've established our extremes all the way here at saturation, all the way here at cutoff. Draw a line between those two. And now we've established all possible points of operation for our transistor given its circuit that it is currently in. However, we are at a specific point of operation given that we are biasing it here with this 130K and 30K, and we have nothing else happening to this circuit right now. That will change next class where we add something to this exact circuit. Okay, and so our current operating point is at 10.06 volts with 1.26 milliamps flowing through the collector. Well, 10 volts is, let's say this is the halfway point at 12 volts, so a little before that. Let's say right about here. We are at 10.06 volts, and we should get a little more than halfway between 0 and 2.2 milliamps. Sure enough, we do 1.26 milliamps. And here is our current operating point, or our quiescent point. Okay. So that's the approximation technique. I think this is vastly quicker and faster than that Thevenin solution that we covered last time. And those are the only two DC solutions that we're going to cover for our basic transistor circuits. Okay, and as I said, the approximation technique does work quite well, and we'll get fairly close to that Thevenin solution, or a more proper solution, especially when this statement is valid and R2 has been selected such that it is much or less than 0.1 times beta times RE. Okay, so easy to do. Okay, now this is all kind of in preparation for solving our first amplifier circuit. Now we need to go ahead and talk a little bit about amplification. That's what I'm going to do the rest of today. So I will be using this same problem as the basis of our amplifier that we're going to do the full solution on next class. But for now, let's go ahead and kind of get some generalized amplifier information, a few of the things we're going to need to know in order to understand what our amplifier circuit is doing next class. Okay, so transistors as amplifiers. Okay, now let's go ahead and let's just reduce all of the circuitry stuff and just talk about a transistor. Okay, and if you think about it, if I have both the input and the output referenced to ground over here, you can think of this transistor as having an input and having an output. That's exactly what we're going to be doing. Now, our input in this case is really just the base current. And the output is actually the collector current flowing in this direction. And so if you go ahead and think about our input and output, you can apply a small signal to our input, and we know we have this natural gain of this transistor. The natural current gain of this transistor is what we've been referring to as beta. It's a factor of typically around 100. So if I apply some input here, I'm going to get 100 times that input in the form of the collector current. Now, the output obviously is not drawn to scale, but we know that the output is going to be much larger than IB by beta. Okay, now because our input and our output are sharing this point, in fact, they're sharing the emitter. The emitter is common to both the input and the output. So this type of amplifier, our first amplifier that we would be looking at, is known as a common emitter amplifier. Now, so our emitter is common to both the input and the output, hence the term common emitter amplifier. However, it is a little, let's say, screwy to be talking about our inputs and our outputs in terms of currents. Typically, the thing that we want to amplify is voltage. If you think about, say, taking input into some embedded system, taking input into an analog digital converter, processing. If you think about processing a value and getting it into your computational system, whatever that system may be, typically you're working with voltages. So if you think about a small signal sensor over here, something like a temperature sensor, something like a sound input, it's usually the voltage that we want to make much larger, not just current. So we're going to need to convert our voltages to currents in order to get our input and output to be in terms of voltages. Well, not hard to do. We can always turn a voltage into a current or a current into a voltage just using a resistor, right? By that relationship of Ohm's law. So we're going to go ahead and modify this a bit. We're going to add a series resistor here to convert the voltage into a current, and we're going to add a resistor over here in order to convert that current, the collector current, into a voltage. So now we have an input in terms of a changing voltage, hence the diagonal arrow that I've put through the voltage source over here, and I've labeled it as VBB for our base bias voltage. And so you can think of this varying voltage as that signal. And similarly on the output, now our output is actually VCE, or the voltage drop across here, which changes as the current flows between VCC and the collector, and then eventually to this emitter over here. So we have now an output in terms of a voltage. Ooh. Just imagine this is a larger sine wave of some kind. Okay, and so now we can talk about RB and RC. We have our IB and we have our IC. And we can go ahead and now talk about our input voltage. VBB is going to be equal to, well, IB times RB plus VBE. So I've just written out a KVL expression for our input, VBB, and similarly our output. VCE is going to be equal to VCC minus IC times RC. And now let's go ahead and talk about the relationship between our input voltage VBB and our output voltage VCE. Now, if you notice, this is our base bias circuit, right? Right after our base bias circuit, we learned the voltage divider bias. So we will eventually be building this up into our voltage divider bias, which is a pretty good circuit because, like I said previously, our voltage divider bias negates those changes to beta, and then it allows us the flexibility to just control the gain based off of the resistors, so we don't have to worry about beta changing on us and changing what our gain of the amplifier is. So let's go ahead and talk about the relationship between our input and our output voltage. So I'm going to say if VBB increases, what does IB do? That's a question for you guys. If VBB goes up, what happens to IB? I have a larger voltage being applied to this resistor. Does IB go up or does IB go down if VBB increases? Yeah, right? It goes up. Okay, if IB increases, what happens to IC? Does IC go up or does IC go down if IB increases? Are you sure about that? It goes up, right? Because the relationship between the base current and the collector current is that factor of beta. So if IC is equal to beta times IB, then if IB goes up, IC is just equal to 100 times IB. So they are proportional to each other. So IC increases. Okay, if IC increases, what happens to the voltage drop across RC? In other words, what happens to VRC? Yeah, it goes up as well. So VRC increases. You see where I'm headed here. Okay, if VRC increases, then what happens to VCE? VCE decreases, right? So as VBB increases, the base current increases. As the base current increases, the collector current increases. As the collector current increases, the voltage drop across RC increases. And if the voltage drop across RC increases, then VCE has to decrease because we have to maintain this constant voltage across here, right? So by KVL, VRC and VCE end up being inversely proportional to each other. Okay, so that's what happens as our voltage applied to the input goes up. What about if the voltage on the input goes down? If VBB decreases, then IB has to decrease. And see, it's just going to be the opposite of the above statement. If IB decreases, then IC decreases. If IC decreases, then the voltage drop across RC decreases. And if the voltage drop across RC decreases, then the voltage drop between the collector and the emitter must go up. Okay, so what that means here, VBB goes up, VCE goes down. And if VBB goes down, VCE goes up. I lied here. As far as VCE is concerned, as VBB goes up, we're going to get an amplified yet invert. Oh, I'm looking at the wrong screen here as I draw this. There we go. Okay, my sine wave's got some distortion. That's okay for illustration purposes. So as VBB goes up, VCE goes down. So it's going to be amplified, but it is going to be inverted from our input. So that's the first important thing to know about the relationship between our VBB input and our output being VCE. Okay, so this is the idea of how we're going to use a transistor to get an amplified signal coming out of it. Okay, now there's a bit more. Let's go ahead and talk briefly about two things that any signal is created from. any signal has these two components. The first one is going to be the AC component, and the second one is this DC component. I think this will make sense once I go ahead and draw it. Let's say I have some sine wave at some value. If you notice, this is centered at some value other than 0. And so the DC component is what we refer to as this DC offset. DC offset is just the quantity by which we are centered at from 0. So if this center was, let's say, 10 volts, then our DC offset is equal to 10 volts, and this is our DC component. However, that's not the only thing that describes this sine wave. We also have the amplitude for our AC. How much does it go up and down relative to our DC offset? So our AC component would be however you want to describe the peak-to-peak voltage here. You could talk about it in peak voltage, you could talk about it in RMS voltage, but nevertheless our component So as I said, you could talk about this in terms of RMS or peak-to-peak voltage. Okay, so that's our AC component and our DC component. And we're going to have to work with both of these to construct our first useful amplifier. Now, our DC offset over here is responsible for placing us somewhere on this load line. If you notice this DC offset over here, if we were at 0, what happens to our transistor if this is at 0? How does our transistor operate? What mode of operation will it be in if VBB is 0? It's in cutoff, right? Well, if we're at cutoff, which is down here, how do you expect to go any lower than 0? You can't. Okay, so we have to live with this DC offset because this DC offset places us somewhere along this load line. Similarly, if our voltage is too high, if our DC offset, I should say, is too high, then we're going to be on the top portion of this load line. So with too large of a DC offset, how do you expect to get any larger than saturation? You can't. We're limited in how much direction we can move this Q point in this direction. Similarly, we're limited on how much we can move the Q point in this direction. So we have to have some DC offset. We have to live with this because it's what controls that keeps, I should say, keeps our transistor within this linear region. So we can only amplify, we can only have a useful amplifier if we stay within this load line or we stay within this linear region. So what happens, if you think about it, as this signal goes up and goes down, and goes up and goes down, as it goes up, this Q point goes up, and as it goes down, the Q point goes down, and as the Q point goes up, as our applied input signal goes up, our Q point slides up. So we're constantly sliding up and down in relationship to our applied input signal, but we start with our Q point at some centered point here, which is our DC offset. So let's go ahead and look at what happens if our Q point is too low to start off with. In other words, if our DC offset is too small. And then we'll look at the case when our DC offset is too large, what happens to this Q point. So you can think of our applied signal causing this Q point to slide up and down. Similarly here, you can think of our Q point as sliding up and down. So we need to make sure that we have enough room to go up, and we need to make sure that we have enough room to go down. If we don't, let's say over here we got a very small DC offset. If you notice over here, we're dipping way below the 0 point. When we dip below the 0 point, our output, which our output would be VCE, is going to get cut off. Now our output is inverted from our input. It'll be able to go down, but when it comes back up, it's going to reach a point that it can't get any further. our signal should have been allowed to go up, but because we hit cutoff mode, it's unable to do so, and so it just flat lines. We call this distortion. Now, distortion, if you're talking about an electric guitar, sounds awesome. We love distortion when we're talking about an electric guitar. But if we're talking about trying to keep a signal intact for the case of measurement, for the case of our applications and computation, then this is terrible. We don't want to do this. Similarly, if we start off with too high of a DC operating point, then our DC offset is way up here. And our output will also have some problems. When VCE goes down in response to our collector current going up because our applied voltage is increasing, then we will have hit saturation, and again we flatline over here. We should have completed this, but we hit saturation when our applied signal caused the cue point to shift into the saturation region. So again, this leads to distortion, which is great for a guitar, but terrible for us. Okay? So for this reason, it's nice to see the load line and ensure that we are at its optimal place. So there is, for the case of designing an amplifier, there's an optimal position for this cue point.
So if you want nasty distortion for your electric guitar, make the crappiest amp possible.
Yes.
Okay.
That's exactly how it used to be done. Well, it's kind of still done that way, but you know how that button's called, or that dial is called overdrive on your amp?
Uh-huh.
What you're doing is you're making the signal before it hits the main amplification stage. You're making it much larger than the amplifier can deal with, and so it gets clipped off and sounds awesome.
Sounds like it would damage something.
Surprisingly not. No, because your transistor doesn't care. I know it sounds like, oh, you're overdriving, you're giving it a lot of power. No, you're just making that input signal larger than the amplifier can deal with, and so the vacuum tube or the transistor just saturates, and it's like, nah, I can't go any higher.
Okay, so it's still within like a safe amount of current for that to operate.
Yeah, this is why with like older amps, if you notice, they don't sound right unless they're really loud.
Yeah.
That's why. Is because in order to achieve the distortion that makes your guitar sound good, you actually have to have it loud enough in order to clip that amplifier.
I see.
Yes, I said that correctly. Sorry, I gotta think in my head. So yeah, that's why old school, especially old school amps. Now, when you're talking about creating those effects digitally, it's like, oh, okay, I can create them at lower volume levels, but you know,
that's not fun.
Yeah, I guess. Okay, so optimum cue point. Hopefully, if I tell you I don't want to be too much towards saturation, I don't want to be too much towards cutoff. Where's my optimal point? Yeah, it's right here, right? It's in the middle. And I'll go ahead and put one little caveat. Optimum cue point for an amplifier, right? That gives us the most amount of range before we hit saturation. It gives us the most amount of range before we hit cutoff. Okay, so generally speaking, when we construct our amplifiers and you go through that DC analysis and you do the load line at the very end, the whole point is to ensure that we are actually in between saturation and cutoff. Try to get as close to the middle as possible when you're designing these things. And so now hopefully that load line sort of makes sense, because I think before we were just doing it as an academic, hey, we call this a load line and this is what we do. Now you can kind of see the purpose behind it, because if you don't draw this load line, I don't know how you're going to figure out how close you are to saturation and cutoff. This is a great way to visualize that. Okay, so the load line is an incredibly valuable tool for analyzing where our transistor is biased for the sake of constructing an amplifier. Now, that being said, when we talk about an output coming out, if we talk about an output coming out from a sensor, right? If you think about the sensor providing a signal, we can always model a sensor as a variable voltage with a series resistance. When we talked about, in 211, when we talked about the maximum power transfer, and you learned that there was an internal resistance to your battery, well, that exists for any voltage source, and sensors are no different. When you construct a circuit to behave like your sensor, you have a variable voltage. You essentially have a voltage that's going to go up and down in regards to what that sensor is measuring, and you have some resistance in that circuit. And so you can always model it like this. But keep in mind that we have to live with this idea that we want our DC offset to be right here in the middle where our transistor is being biased. Well, our sensor does not know that we are connecting it to an amplifier that has a DC offset where our cue point is right in the middle. It doesn't care. We just have some changing voltage, and this could be centered around 0. This could be centered off at 20 volts. It could be centered at minus 10 volts. But we want to feed this into our amplifier at some point. So we're going to want to remove the DC offset. And so how can we remove this DC offset? If we talk about the signal as having two components, our AC component and our DC component, we can actually feed this directly through a capacitor And what's going to happen is we're going to strip out this DC offset. This DC offset effectively gets removed and our signal gets centered at 0 volts now. The AC component can get through, but the DC component cannot get through. So as far as this capacitor is concerned, if I stick this capacitor in series with any changing voltage, I'm going to allow the AC to get through and the DC is not going to be able to get through. Now, why is that? Well, let me give you the correct explanation first. Everyone's now thinking, what's the incorrect explanation? You'll see in a minute. So capacitors have something referred to as capacitance. Did I write capacitor reactance? It's capacitive reactance. Has some capacitive reactance. Okay. We call it X sub C. Now, what is capacitive reactance? It's resistance. So this capacitor does have some resistance, but it's dependent upon frequency. The capacitive reactance is given by the equation 1 over 2 pi F C. So it's dependent upon the frequency of the applied AC. So if this is 1 hertz, 10 hertz, a kilohertz, it depends on the frequency and the value of the capacitor. Now, if we go ahead and plug this in for a large enough frequency, you'll see that the capacitive reactance goes to 0, right? If I make this value for frequency sufficiently high enough, the capacitive reactance, which is given in ohms, appears to be 0. Another word for 0 ohms, short, closed switch. Allow the AC to get through because it has frequency, and I'm assuming that the frequency is sufficiently high. Similarly, if I solve capacitive reactance for DC, what's the frequency of DC? Zero hertz. In other words, infinite ohms. Another word for infinite ohms, open switch. So this capacitor will not allow the DC to go through. In other words, it'll behave like an open switch here. But for AC or sufficiently high enough frequency, this capacitor is going to behave like a closed switch and allow the AC to go through. That's the correct answer. What's the incorrect answer?
Magic.
DC hits the wall. AC is allowed to slip through.
Will this be valid on the midterm?
No.
Okay.
but the symbol does kind of say this. The real answer is because of the capacitive reactance. Okay? There is one more step that we have to do. Because once we put it in series with this capacitor, yes, we strip out this DC component. And you get your signal centered at 0 volts. Absolutely true. However, this isn't good for our transistor amplifier circuit that we want to make either, because now we're back to doing this where we're too close to cutoff. And so our amplifier won't be able to operate here. So what we can do now is provide this AC signal our own DC offset. Ooh. In other words, the optimum Q point. Okay, so this is how we can go ahead and create an ideal situation for our amplifier. We can take any signal regardless of where its DC offset is. We can remove the DC offset with a series capacitor because its capacitive reactance is going to cause the cap to block DC while permitting the AC to get through the capacitor. And then we're going to provide our own desired DC offset, which is going to be the center of the load line or our desired optimum Q point. Okay, and so once you go ahead and put this together, we are now taking our signal and then more than likely we're going to want to remove that DC bias yet again, because the chances that our output wants the same DC offset that our amplifier requires in order to operate and not distort by cutting off in one direction or the other, that likelihood is very small that those two are going to be equal to each other. And obviously these are all tied to ground here. So they are all in reference to the same 0 volt point. And so this would be an acceptable amplifier circuit right here. We take our input signal, we strip out its DC offset. In this case, it's actually centered at 0. But regardless, we would still have a capacitor in series here. You give it your own DC offset, which should be at the optimal Q point, and then you go ahead and feed this in here, and then you remove the DC offset that was required for amplifier operation, and now you get a nice amplified voltage that's centered at 0 volts. And if you needed this to be different than 0 volts, then again you would go ahead and apply a voltage here in order to shift this signal up or down. Okay, now for reasons that we spoke about, the base bias transistor circuit is not a very good circuit because of its dependency upon that value of beta. And for that reason, we will be using a voltage divider bias. Now, I'm going to go ahead and do the full solution for the voltage divider bias common emitter amplifier next class, where we put all of these principles together and solve for what we're most interested in as far as the amplifier is concerned. Okay? So with that being said, let's go ahead and stop here. Let's take a 10-minute break. We'll return to lab, and we need to finish up that real simple transistor lab. Okay? Okay, so for the lab, you should have already solved the 2 circuits, and we're only dealing with the NPN version over here, where we have 5 volts applied, and then we're going to apply either 0 volts or 5 volts to this, and ground attached to this transistor. So this is just using the transistor as a switch. And let's go ahead and take the measurements. Okay, so what we're going to do now is we're going to step through this procedure that they have outlined on the lab. Connect the circuit in figure 27-2.3. Apply the correct polarity of voltage to VCC over here, which is going to be 5 volts. So we want a 1K ohm resistor, and we want a 10K ohm resistor, and we need a NPN general purpose transistor. Okay, so let's go ahead. Let's list out these components, 1K and 10K. Switch back over here. Okay, we're going to need a 1K. We're going to need a 10K. And we need some general purpose NPN transistor, which is going to be the 2N3904. And I should have a few in here. In fact, if I randomly pull any one of these, hey, look, first pick, 2N3904 right here. Okay, now we're going to need our 2 resistors. So I'm going to go ahead, open up my box, and let's look for a 1K. And we're also going to need a 10K. And that should be everything that we need. Everything else will be connections on the breadboard. So I'll go ahead and grab some breadboard wires. And let's clean up this breadboard. And now what we're going to need is some power to come in. So I'm going to take this from my benchtop power supply. And my 5 volts will be coming in on these two cables over here. Okay, and I just flipped it on. We are set at 5 volts. So what I'm going to do is I'm going to give ourselves minus on both of these rails, and I'm going to give ourselves the positive 5 volts on both of these rails, just so that we have convenient access to any voltage that we may need. In fact, I'll set this up on this side. Okay, that takes care of the positive rail. And for the negative rail, I'll do the same thing. Okay, so now I have our minus attached down here, and I have our positive attached on both sides. Now I need 2 more wires. So I will do positive attached over here. And I'll do our negative attached down here. And now I have 5 volts and minus on both of these. Now we do want to attach our circuit just like we have in this image over here. I'll just move myself out of the way. Okay. So we're going to have our V in go to this 10K, which goes to the base of the transistor. We have our collector attached to the 1K, and we have the emitter attached to ground. Okay. So we need to figure out how to translate from this transistor to our schematic. Now our transistor, let me go ahead and draw this out. Has 3 legs, and this package is known as a TO92. The TO92 is one of those ubiquitous packages that gets used a lot for basic components like this. So if you go ahead and do a search for a 2N3904, I'm just going to go with the most convenient, which is an image. Oh, it doesn't show the, here we go. Okay, so you can see over here it goes from left to right. So if you put the flat side of the transistor towards you, it goes E, B, and C, emitter, base, collector. So let me switch back over here. Emitter, base, and collector. And we want to set up our circuit. So we have a 10K for the base resistor, 1K for our collector resistor, 5 volts applied there, ground down here. Okay, so if I look at this from left to right, E, B, and C. Okay, so right now the way I have it, with the flat side, the bottom leg is our emitter. The left leg I bent out was the base, and the top one is the collector. We want the collector tied with a 1K to 5 volts, so I'll find my 1K. 1K is brown, black, black, brown. So the last brown is 1 for the number of zeros. That's our multiplier. And so 1 followed by 3 zeros. And we want this tied up to 5 volts. There we go. Nice and clean. Okay, and our base is going to have a 1K in series with it. So I will share the same group of 5 with the base terminal of our 2N3904. So now I have my input on this side. I have the 1K tied up to 5 volts as I have attached over here already. And the bottom side, the emitter of our transistor, needs to be tied to ground. So I will use this cute little jumper. I much prefer these wires and jumpers to, say, those prefabbed connectors. If people have experienced this yet, those prefabbed connectors that come with those Amazon breadboard kits are pretty bad. Those wires snap off. I had somebody in my 262 class say that they couldn't even pull it out of the breadboard without it breaking. Unfortunately, I'm not in quality control for those breadboards and those breadboard kits. But I can tell you from experience, these types of wires work a lot better. You can always just buy a spool of wire and then cut and strip these to length. In fact, maybe I'll just do that here to show how easy it is. Just snip whatever length you want, strip off the ends. These are my favorite pair of wire strippers. They're made by Greenlee. They used to be made by Palladian, and you can find those. I do have that listed under the supplies page of my website as being my favorite inexpensive pair of wire strippers. And then you can make your connectors like this, bend them however you want. And it goes in like this, or you can also find these on Amazon. They're usually sold separately. You may find a kit that comes with these. If you do, I actually much prefer these, and I tend to use these just to make life a lot easier because they come in different lengths. They're already stripped. And I picked one that was a little too small. Here, I'll use this blue one over here. And a pair of tweezers comes in very handy for putting things into breadboards without damaging items. Just gives you a little finer control. Okay, so that's our circuit. We're done. Okay, let's go ahead now and look at what's next on our lab. Connect point A to ground. Aha. Connect point A. Point A is our input. So we want to connect our input voltage to ground. Measure and record the voltage from point B to ground. In other words, VCE. So we're going to take this guy to ground, and we're going to measure VCE. Okay, to do that is really easy. I will just use this longer yellow cable to go from the input of that 10K resistor, and then I will just attach it to ground. We have our +5, we have our minus side of our 5, we have our input tied to ground, and now I can just go ahead and measure the voltage between that point B and ground. Okay, now here's my first question. You calculated this by hand. Our input is tied to ground. What should the voltage drop be between the collector and the emitter? In other words, what should VCE be?
5 volts.
So you think it should be 5 volts. And I'm assuming with this is tied to 0, then we have 0 for the base current. If we have 0 base current, this transistor should be in cutoff. If this is in cutoff, then it is open between these 2 points. We have no current flowing through this 1K, therefore no voltage drop, so we should be measuring the entire 5 volts between these 2 points. That is the prediction given by, was that Justin?
Yes, sir.
Sweet, thank you. So, let's see. I'm going to set this to voltage. And for the most convenient, best way to make these measurements on a breadboard, I always go where the conductor actually inserts into the board, and I put one probe there. Now, you can't just do this on an empty row of 5 because you have plastic insulating your probe from the connectors that are below. However, when you have a conductor sticking out of it, it makes a great place to hold the tip of your probe so that you can go ahead and do the same thing with the other probe and very easily measure, look at that, 5 volts. Okay. So at least Justin's solution is correct. Why did I say 0 over here? Nobody caught me on that one. I wrote 0 over here after I said the transistor was in cutoff. We had 0 current flowing through here, so we should measure the entire applied voltage of 5 volts. Okay. And we did, sure enough. Okay, so that takes care of step 2. The answer was 5 volts. Now for step 3, connect point A to 5 volts. Measure and record the voltage from point B to ground. So again, let's look at VCE. So now what we're going to do is we are going to take this input, we are going to tie it up to 5 volts, and we're going to measure VCE. Okay, what do you guys think we're going to get for VCE? Well, first off, if we tie this to 5 volts, is our transistor going to be in cutoff mode anymore? No, we're going to get some current flowing into the base. If we get current flowing into the base, it would be 5 volts minus 0.7 volts. Gives us the voltage drop across that. Divide that by 10K. That gives you your base current. Your base current multiplied by 100 for the beta of this transistor gives you quite a bit of collector current. You're going to come up with the solution exactly that our transistor is now saturated. Plug in the saturation model, you're going to get a 0.2 volt drop between VCE. Okay, so when I have it tied up to 5 volts, my predicted value would be 0.2 volts, and I've written this in red, whereas when before in the previous step we had it tied down to ground with in black, and that gave us 5 volts. So we should get 0.2 volts through there. Now this is for the board model. This is for the model that we're using. I suspect we are going to be better than 0.2 volts. And when I say better, I mean more saturated. The most saturated that we could possibly get is 0 volts. If we are closer to 0 volts, I'm happier because this transistor is acting more like a closed switch. Worst case would be 0.2 volts, which is still a closed switch, just not that great of one. So let's go ahead now and let's take our input, and now let's tie this to 5 volts. And let's measure what we get between the emitter and the collector. 0.04 volts. That's fantastic. I just can't write voltages today. Okay, so we measured 0.04 volts. Well, this transistor is definitely saturated. We saw it go from 5 volts to 0.04 volts, or like a closed switch where we have 0 volt drop across there. Okay, so that would be the answer to 3. Okay, cool. So this is definitely working. Now the next steps that are in the lab were for figure 27-2.4. Now that's this transistor, which is the PNP. I'm not going to cover the PNP transistor. The only difference is, if you notice, it's minus 5 volts up here. If you notice, the direction of the arrow on the emitter is pointed upward. So if I have a lower voltage up here than ground, which I do, minus 5 versus 0 volts over here, then the current's going to be going upward. So a PNP essentially is the same as an NPN. It's just that all of your values get negative signs in front of them as opposed to positive signs. Okay, but generally speaking, for our applications for embedded systems, most of the time we're going to be using an NPN transistor, and I don't want to take up the class time doing every single thing with a PNP as well. So we won't do the PNP version of this. But let's see if we can make something a little more interesting with this circuit. How about if I switch an LED on and off with it? So let me go ahead and grab my parts tray of LEDs. I got green, I got red. I'll just go with green. I'm going to switch that 1K for something closer to, let's say, 330 ohms. That should give us a higher voltage. Now, when you're using an LED, remember you're going to get a 1.8 voltage drop across him. So we want to lower the value of the resistor so we can increase the current that would be going from the collector to the emitter. So I'm just going to go through my junk resistor pile and find something that's close to 330 ohms. I found 33 ohms. Uh, 330 ohms. $22K. And if I don't find one in here, I'll go back to my box. All right, fine. Okay. So I now have something closer to 33. Actually, I do have 330 ohms. And then the longer leg of the transistor should go up to the positive, and the other side. Oh no, it's not supposed to be on yet. There we go. So now if I attach this to ground, it should be off, and it is. If I attach this to positive, it should be on, and it is. Off, on, off, on. Okay, cool. Now the nice thing about this circuit is that the current going through the LED is not coming through the yellow wire, right? It's coming from the top of this LED. So if you're working with an embedded system, if you're working with an FPGA, a microcontroller, then you would like to not have the current go through this yellow wire, because this is coming from your 8051 or your ARM processor. And so the amount of current that's actually going through this is quite small. And you can go ahead and calculate that. let's say 5 volts minus 0.7 gives us a 4.3 volt drop across that resistor, and that resistor is 10K. So 4.3 volts divided by 10K is 0.4 milliamps. So we only have 0.4 milliamps coming from, or going through the yellow wire, or being sourced by our 8051 or our microcontroller or our FPGA. So that's a great situation to be in. So in this case, this transistor is behaving like our driver for the LED, such that we don't need to source that current from our digital devices. And this is incredibly convenient, powerful, and necessary to do in most embedded systems for most of your pins. Okay? So with that being said, that's it for the lab. You have your values recorded. Did I miss anything?
Oh, Professor?
Yes.
For